To predict molecular reality from pure mathematics, we have to analyze the system at the deep quantum scale, where electrons constantly fluctuate around a nucleus. The conventional starting point is the many-electron wave function, psi. But for practical simulation, this creates an immediate computational bottleneck. Because the wave function depends on the coordinates of every electron simultaneously, its complexity scales exponentially. For a system with n electrons, you are forced to solve for 3n spatial coordinates, plus spin. Density functional theory, or DFT, provides a theoretical framework designed to bypass this 3n-dimensional problem entirely. The core mapping theory of DFT proves that the exact ground state energy and physical properties of a molecule can be determined strictly from its electron density, rho of r. Mathematically, this relies on a functional. While a standard function maps a number to a number, a functional maps an entire function, in this case the 3D density, to a single scalar value, the total energy. By proving that E equals E of rho, DFT collapses a massive multidimensional problem into a manageable 3D space. This dimensional reduction is what makes quantum calculations of large materials computationally tractable. This dimensional reduction was formalized by Walter Kohn, a breakthrough that earned the Nobel Prize. However, while the theorem proves the exact energy functional exists, it does not reveal the actual mathematical equation. This creates the primary engineering challenge. Scientists must construct a practical, programmable framework to approximate this missing relationship. To understand how that works, we need to look at the specific mathematical architecture required to turn a raw 3D electron density into measurable observables like vibrational spectra and molecular geometries. The bridge between abstract theory and a solvable framework is the Kohn-Sham approach. It replaces the real system of interacting electrons with an imaginary system of non-interacting particles. Instead of repelling each other, these particles move smoothly through a single effective potential field. To remain physically relevant, this fictitious system is engineered to yield the exact same ground state electron density as the real interacting system. This density is constructed using mathematical tools called Kohn-Sham orbitals. For closed-shell systems, the total electron density is calculated by summing the absolute squares of these spatial orbitals and multiplying by 2 to account for spin. Introducing these orbitals allows the system to accurately calculate the kinetic energy, providing the final component needed for our master energy equation. The total Kohn-Sham energy functional maps out 4 distinct physical forces. 3 of these are known variables: the non-interacting kinetic energy, the nuclear electron attraction, and the classical Coulomb repulsion. That leaves one final, unknown term, the exchange correlation functional. Because the Kohn-Sham system is non-interacting, this term is forced to absorb the missing quantum effects, specifically quantum exchange and dynamic electron correlation. Consequently, the accuracy of any DFT calculation depends on how well scientists can approximate this single exchange correlation term. Functional approximations follow a hierarchy of complexity, starting with the local density approximation, or LDA, which calculates energy based only on the density at a specific point. The generalized gradient approximation, or GGA, adds accuracy by analyzing how quickly the density changes across space. Higher up the ladder are hybrid functionals like B3-Lewipe. These mix DFT calculations with exact Hartree-Fock exchange to improve predictions for thermochemistry and reaction barriers. Further specialized adjustments include range-separated hybrids for charge transfer states and dispersion corrections to account for weak van der Waals interactions. Regardless of the functional chosen, these equations are solved through a self-consistent field cycle. The computer starts with an initial guess and loops through the calculation until the electron density stabilizes. Running a DFT job requires selecting the functional that best matches the target system and iterating the cycle until the density converges. Static energy values are only the beginning. To understand a molecule, we need to know how that energy changes when the nuclei physically move. This change is found through the gradient. Mathematically, the first derivative of energy to nuclear coordinates corresponds to the physical force on atoms. This force drives geometry optimization. Software moves atoms down the energy slope until the gradient reaches 0, finding a stationary point. This first derivative is what allows the system to take a rough molecular sketch and automatically relax it into its stable physical structure. To analyze that structure, we look at the Hessian matrix, defined as the second derivative of the energy. The Hessian describes the curvature of the potential energy surface. It determines if our optimized geometry sits in a stable valley or on a mountain pass. A local minimum shows positive curvature in all directions, while a transition state has exactly one negative curvature direction, representing a reaction barrier. Software uses analytical derivatives to extract these values directly from the mathematical form of the method, ensuring they are faster and more accurate than numerical estimates. Because electron orbitals respond when nuclei move, the system must also solve the coupled perturbed Kohn-Sham equations to account for the shifting electron cloud. These derivatives map directly to laboratory data. Hessian curvature yields vibrational frequencies for IR and Raman spectra, while derivatives against electric fields provide dipole moments and polarizabilities. In research areas like organic electronics, these calculations determine reorganization energy and non-radiative decay pathways, which dictate the efficiency of devices like OLEDs. This entire architecture, from the density functional to the analytical derivatives, converts quantum probabilities into the predictive data required to engineer new materials.